In this module, we will look at the analysis of epicyclic gear trains. Recall that in an epicyclic gear train, the gear may be on a shaft that may itself be moving. For example, for the gear train shown on the left, the gear B is on a shaft that can itself revolve or move. For the gear train shown on the right, the gear 3 or the planet gear is on a shaft that can itself revolve. There are many types of epicyclic gear train, namely simple epicyclic gear train, reverted epicyclic gear train, ring epicyclic gear train or planetary epicyclic gear train, and compound epicyclic gear train. In this lecture, we will look at the analysis of the first three types. And remember, a reverted epicyclic gear train is also a compound epicyclic gear train. The picture on the left here shows a simple epicyclic gear train. The middle picture shows a reverted epicyclic gear train. And the picture on the right shows a ring epicyclic gear train. In all of these gear trains, you will see that there is an arm present. In the simple epicyclic gear train, if you remove this arm or fix this arm, the gear train that remains is a simple gear train. That's why we have the name simple epicyclic gear train. Similarly, in the gear train in the middle here, if I remove this arm or if I fix this arm, I have a reverted gear train. Therefore, this is called a reverted epicyclic gear train. Epicyclic gear trains has 2 degrees of freedom. So you have to specify 2 inputs. For example, in the picture on the left, we can specify the motion of the arm as well as gear A or gear B. In the ring epicyclic gear train on the right, we can specify the motion of the arm and the ring gear. In previous parts of this lecture, you have seen the simple gear train and the reverted gear train, but you haven't seen the ring gear train. The gear in the middle is called the sun gear, the gear 3 is called the planet gear, and the outer gear is called the ring gear. There is usually more than one planet gear, and a better picture of the epicyclic gear train is shown here. These 4 gears here are the planets, the middle gear is the sun gear, and the outer gear is the ring gear. The arm is not shown here. The key advantages of epicyclic gear train is that very high ratios are possible in very small packages. These gear trains can be naturally reverted, and 2 degrees of freedom allows that you can have multiple velocity ratios without gear disengagement. Furthermore, you can have differentiation, which means that the output shafts can have different angular speeds such that their average is the speed of the input shaft, and you can have multiple output shafts. If properly designed, epicyclic gear trains can also have very high efficiency. They are quite often used in high-performance motors and in automobile transmissions. Let us now delve into the analysis of epicyclic gear trains. We will first look at a simple epicyclic gear train. An example problem is given here. In a simple epicyclic gear train shown here, the arm C carries the 2 gears A and B. The number of teeth on gear A is denoted by NA, number of teeth on gear B is denoted by NB, and NA is equal to 36 and NB equal to 45. The arm rotates at 100 RPM in the clockwise direction. If gear A is fixed, what is the angular velocity of gear B? And the second question says, if gear A rotates at 200 RPM clockwise, what will be the speed of gear B? As I told you before, epicyclic gear trains requires 2 inputs. You will see that in the problem A here, the 2 inputs are the speed of the arm and the fact that the speed of the gear A should be 0 or it is fixed. And in the part B, the inputs are the speed of the arm and the speed of gear A. We will use a tabular method to analyze epicyclic gear trains, and we will use the method of superposition to create the table. The technique that we will be using will be applicable to all the types of gear trains that you will study. So let us first understand the technique using this simple example. First note that if we fix the arm C, then A and B form a simple gear train. Therefore, omega B by omega A equal to minus NA by NB. I have the negative sign here because A and B form an external gear set. Now if omega A equal to 1, that is I just give 1 revolution to gear A, then omega B equal to minus NA by NB. So this will be the starting point of our tabular method. We'll assume the arm will be fixed and gear A will rotate through +1 revolution. This will be our applied motion. And here we will write down the moving elements. We have 3 moving elements: the arm, the gear A, and the gear B. So arm is fixed, so I have 0 for the arm. Gear A is given +1 revolutions. Then gear B will rotate by -NA by NB. So if I rotate the gear A by X revolutions, gear B will rotate by -X times NA by NB. Now I will assume that the gear A and B are locked with respect to each other, and I am giving the arm the motion. Since the arm carries gear A and B, this will boil down to adding +Y revolutions to all elements. So I add +Y to each one of the elements. So my total motion will be Y for the arm, Y plus X for the gear A, and Y minus X times NA by NB for the gear B. I am just adding these 2 rows to get the total motion. Adding these 2 independent motions is the principle of superposition, which we use to get the total motion. Once I create this table, which is just dependent on this simple gear train and is not dependent on any numbers that I put in, I will use the numbers from the previous problem to obtain X and Y, and therefore the angular velocities of the gear B. So from the given data, I have NA as 36 and NB as 45. The arm rotates at 100 RPM in the counterclockwise direction, so Y equal to 100 from the previous table, because the total motion of the arm is Y. When gear A is fixed, since the total motion of gear A is X plus Y, we have X plus Y equal to 0. Therefore X equal to -100. Therefore the angular velocity of gear B is Y minus X times NA by NB, which gives 180 RPM. For the case B, the gear rotates at 200 RPM clockwise. So omega A equal to -200 RPM. Therefore X plus Y is equal to -200. Remember, X plus Y is the motion of gear A from the previous slide. Therefore X is equal to -300 RPM. And omega B becomes 340 RPM. Let us now look at the reverted epicyclic gear train. The gears 2 and 3 are on the same shaft and form the compound gear. The gears 1 and 4 are on concentric shafts, and the arm carries gears 1 and 4 and the compound gears 2 and 3. Gear 1 meshes with gear 2 and gear 3 meshes with gear 4. Therefore, we have D1 plus D2 is equal to D3 plus D4. This implies that M1 times N1 plus N2 equal to M3 times N3 plus N4, where M1 is the module of gear 1 and 2 and M3 is the module of gear 3 and 4. We have seen the derivation here before when we looked at the reverted gear train. And if M1 equal to M3, that is the modules of all the gears are same, then we have N1 plus N2 equal to N3 plus N4. This implies that if we know the number of teeth on 3 of the gears, we can compute the number of teeth on the 4th gear. Now to analyze a reverted epicyclic gear train, we will use the tabular method as before. So first, we will assume that the arm is stationary. Since 1 and 2 are meshing with each other, we know that omega 1 by omega 2 equals to minus N2 by N1. Similarly, omega 4 by omega 3 equal to minus N3 by N4. Now 2 and 3 are on the same shaft, so omega 3 equal to omega 2. So if I assume the shaft with gears 2 and 3 is given one rotation, that is omega 3 equal to omega 2 equal to 1, then I get omega 1 equal to minus N2 by N1 and omega 4 equal to minus N3 by N4. And this will be the starting point of creating the table, which you will see in the next slide. So here again, I have one column for the applied motion and the different moving elements. Because the compound gear 2 and 3 have the same motion, therefore we have just one column for it. And we have one column for the arm, and one for the gear 1 and one for the gear 4. So the first step again is the arm fixed and compound gear rotates through +1 revolutions. So arm has a motion of 0, compound gear 2 and 3 is +1, that is omega 2 equal to omega 3 equal to +1. Then from the previous slide we saw the rotation of gear 1 is minus n2 by n1 revolutions, and the rotation of gear 4 is minus n3 by n4 revolutions. So if the arm stays fixed and we applied plus x revolutions to gear 2 and 3, we get minus x times n2 by n1 here and minus x times n3 by n4 here. Now again, we add plus y revolutions to all the elements, which is shown in this row here. And then we sum up the rows 2 and 3 here to get the total motion. So the total motion of the arm is y, the compound gear 2 and 3 is y plus x, the gear 1 is y minus x n2 by n1, and the gear 4 is y minus x n3 by n4. Again note that this table is very general. It doesn't depend on the speeds, it doesn't depend on the number of teeth. For the architecture of the reverted gear train that we had in the previous slide, this table always holds. Now we will use this table and look at an example to see how we can analyze the gear train. So let us consider this example here. We have a reverted epicyclic gear train where the number of teeth for gears 1, 3 and 4, that is N1, N3 and N4, are 75, 90 and 30 respectively. We are also given that the arm has an angular velocity of 100 rpm clockwise and the gear 1 is fixed, that its velocity is 0. We have to find the angular velocity of gear 4, and it is also given that the module of all gears is identical. Now note here that we do not know the number of teeth on gear 2, but we can compute it from the fact that N1 plus N2 equal to N3 plus N4, because it is a reverted gear train and all gears have the same module. This implies that N2 equals to 45. Now from the table on the previous slide and the problem data, y is equal to minus 100 because y was the motion of the arm. Since the gear 1 is fixed, y minus x times n2 by n1, which was the motion of gear 1 in the previous slide, is equal to 0. So from here we can compute x, which comes out to be minus 500 by 3. And then the speed of gear 4 is y minus x n3 by n4, which is 400 rpm. So you can see how the same procedure can be used to analyze the reverted epicyclic gear train as well as the simple epicyclic gear train. If we know how to analyze the gear train without the arm, then analyzing the gear train with the arm is just applying the method of superposition. And this is the same idea that we'll be using when we analyze the planetary or ring gear train in the next couple of slides. Let us now look at the epicyclic gear train with ring gears or the planetary gear train. So in this gear train, there is a sun in the middle, there is a planet and there is an outer ring, and the arm connects the sun and the planet. In this system also, there is a constraint between the number of teeth on the 3 gears. Note that R2 plus 2R3 is equal to R4, where R2 is the radius of the sun, 2R3 is the diameter of the planet, and this whole length is R4, which is the radius of the ring gear. So from here we obtain D2 plus 2D3 equal to D4, where D2, D3, D4 are the diameters of the sun, planet and ring gear respectively. Now we know that the module is D by N. So if N2, N3 and N4 are the number of teeth on the sun, planet and ring gear, then M times N2 plus 2M times N3 equals to M times N4. Now in this case, the sun is meshing with the planet, so the sun and planet has to have the same module, and the planet is meshing with the ring, so the planet and the ring has to have the same module. That implies that all the 3 gears have to have the same module. That's why I can put in the same module for all the 3 gears. This implies N2 plus 2N3 equal to N4. So this is the constraint on the number of teeth among the Sun, planet and ring gear. Now, as we have seen before, to set up the table for analysis of this gear train, we have to first analyze the gear train when the arm is fixed. Let omega 2, omega 3 and omega 4 be the angular velocities of the Sun, planet and ring respectively, and assume that the arm is fixed. Then omega 3 by omega 2 equal to minus N2 by N3. Omega 4 by omega 2 equal to omega 4 by omega 3 times omega 3 by omega 2. Now omega 3 by omega 2 is minus N2 by N3 as we have seen above, and omega 4 by omega 3 is N3 by N4. The sign here is positive because gears 3 and 4 forms an internal gear set. Therefore, we have omega 4 by omega 2 equal to minus N2 by N4. So if omega 2 equal to 1, we have omega 3 equal to minus N2 by N3, and we have omega 4 equal to minus N2 by N4. Now this will be the starting point for our table in the next slide. As usual, the first column is that of the applied motion, the second column is that of the arm, then the gear 2, gear 3 and gear 4. So if we keep the arm fixed and rotate gear 2 through plus 1 revolutions, we have 0 for the arm, plus 1 for gear 2, minus N2 by N3 for gear 3 as we saw in the previous slide, and minus N2 by N4 for gear 4. So keeping the arm fixed and rotating gear 2 through plus x revolutions, we have x here, minus x N2 by N3 here, and minus x N2 by N4. Now we'll add plus y revolutions to all the elements, and adding 2 and 3 we get the total motion. For the arm it is y, for the gear 2 it is y plus x, gear 3 is y minus x N2 by N3, and gear 4 is y minus x N2 by N4. Again, this table is completely general and independent of any values of the number of teeth or the speed of the different elements. Now let us look at a numerical example. So we'll be considering the same gear train as we have seen before, and the number of teeth are shown here. So N2 equal to 40 for the Sun gear, the planet gear N3 has 20 teeth, and the ring gear has 80 teeth, which is N4. The arm is moving at 200 rpm clockwise, and the Sun gear is moving at 100 rpm clockwise. So y equal to minus 200, and the motion of the Sun gear is x plus y, which is equal to minus 100. The negative signs come here because we are rotating in the clockwise direction. From here we get x equal to 100, and using the values of x and y and the expressions for angular velocity of ring gear and planet gear from the previous slide, we get the angular velocities of the ring and the planet gear. So you can see that we have used the same tabular procedure and method of superposition to analyze these different types of epicyclic gear trains. This methodology is completely general and can be used to analyze other epicyclic gear trains also. This is the end of our discussion on design and analysis of gear trains.